Hello, you have already learned that if you have a conductor carrying a current I sitting in a magnetic field B, then using your Fleming's left-hand rule, you can figure out that the force of BIL will be acting in the leftward direction. Now we ask the question, why should a magnetic field exert a magnetic force on a current carrying conductor? So we ask ourselves, what is a current? It's a net flow of charges, isn't it? So if you're talking about a metallic wire, then this current must be borne by electrons drifting in the opposite directions. So could it be that a magnetic field is actually exerting a magnetic force, a tiny magnetic force F, on each and every of these electrons because they are moving in a magnetic field? It has to be, right? So now we got to figure out the formula for the magnetic force experienced by each of these charged particles moving in a magnetic field. So let's suppose we have a wire, length L, carrying a current I, experience a magnetic force of BIL. So we are saying that this current is actually carried by charged particles Q, drifting at velocity V through the conductor. So I'm talking about positive charges now, yeah? So I can write big F as big N times little f. Remember, we are saying that the BIL force is actually the summation of all these tiny magnetic forces acting on each and every charge carrier drifting through the conductor. So N is the number of charge carriers in this volume. So if it's the one illustrated here, then big N is just 6 because there are only 6 charge particles in this volume. In reality, of course, big N will be a humongous number with a gazillion number of zeros. Now on the right hand side, I'm going to write I as NAVQ. Does this ring a bell? You learned this in the topic of current of electricity. So N is the carrier density, the number of charge carriers per unit volume. A is the cross-sectional area. V is the drift velocity. Let's work on the right hand side here. I'm going to pull out B, Q and V. So we are left with N, A and L here. What is A times L? Cross-sectional area times the length L. That will be the volume, isn't it? If you take the volume, multiply it with the number of charge carriers per unit volume, what you get is the number of charge carriers. So big N. So we have big N on both sides. Cancel them away. And then ta-da! We got it. We did it. So if you are a charged particle Q moving at velocity V in a magnetic field B, then you're going to experience a magnetic force that's given by BQV. So that's the magnitude. What about the direction? So let's suppose we have a positive charge Q moving downward at velocity V. It's going to experience a BQV force, but what's the direction? We can still use the Fleming's left-hand rule. So index finger points in the direction of the magnetic field. The middle finger is pointing downward, because positive charged particles drifting downward corresponds to a downward conventional current. That's why the middle finger is pointing down. And now your thumb is pointing out of the screen. That tells us that the BQV force is directed out of the screen. What if we are having negatively charged particles? So we have negative Q moving at velocity V, downward. So this time when you use your Fleming's left-hand rule, the middle finger has to point upward. Why is it upward? Because negatively charged particles drifting downward corresponds to a upward conventional current. So stick your middle finger upward. Now your thumb is pointing into the screen. That tells us that the BQV force is acting into the screen. So what have we learned? If you are talking about current carrying conductor, then we talk about the BIL force. And you use Fleming's left-hand rule to figure out the direction. If you are talking about individual charged particles moving in a magnetic field, then we talk about the BQV force. As for the direction, you still use Fleming's left-hand rule. You just got to be careful. The middle finger must point in the direction of conventional current. So if you're having negative charged particles moving downward, your middle finger must point in the opposite direction. Alright, that's all. Ta-ta!